particular differential operator in m variables, so it's multivariate. And I will create special solutions. It's the only thing I will do. And to do that, I will use a bit of algebra. So I will explore an algebraic framework, and I will use Lie symmetries to prove actually the Fueter theorem in an alternative way. Why am I doing this? Because I can find connections with special functions. And special functions are, of course, very important in mathematical analysis. I don't very often use a pointer. Good. Fueter, what Fueter actually did is quaternions. So the algebra of quaternions, which is this particular example of the Clifford algebra, that is where you should situate the classical Fueter theorem. Now the classical Fueter theorem has to do with functions f defined on R4, so 4 variables. I call them t, x, y, z, inspired by physics, time, and then the spatial coordinates. And then the image of this function is a quaternion. So that means that the function f has 4 components. A 0 component, and then 1, 2, 3, and they refer to I, j, k. So the basis for quaternions. They're all complex units, but as you know, I, j is k, and so on, the quaternion relations. So there is a very important notion in quaternion analysis, and that is regularity. So regularity basically says that the function that you are describing is a solution for a specific operator, the operator dq. What is the operator dq? I wrote it down here. So partial t, x, y, and z, those are just partial derivatives. But you add here the number 1, which we don't often write, and then I, j, and k. So this is a differential operator. If you think about it, it is h-valued, and it maps h-valued functions to other h-valued functions. And what I will talk about is basically this equation. I want to find null solutions for this equation here. Now, I very often need a different way to write down a quaternion, like a quaternion Q here. You can write it in this special way. Actually, it's so important that I will write it here. So a quaternion Q, which is T, and then yx, and then jy, and then kz. What I will do is to write it as T. I keep the T. Now, this is a vector in a 3-dimensional space. So this basically sits in R3. So what I do is to write it as a norm times a unit vector. So the omega is a unit vector. Omega belongs to S2. It's the unit sphere. So this is just polar decomposition. Polar. So it's another way to write down a quaternion. This would be like Cartesian basis. This would be polar, but only for the last 3 components. The first one I keep. I need that in what follows. Mind you that there is recent interest in quaternionic analysis. First of all, there is a series of papers by Frankel and Liebenier, and that is in theoretical physics. These 2 papers here, which I found in the archive, very interesting papers, not easy to read though, but they explain a link between quaternionic analysis and Feynman diagrams. Representation theory, so it's very algebraically, minimal representations, Schrödinger model, so it pops up in quantum mechanics. That is one recent application. There's a whole business on functional calculus and spectral analysis. That is the Italian school, I say, Colombo, Sabatini, Struppat, they initiated. Alpaio recently, and then many other people. Quaternionic Fourier transforms, that's another field in mathematics where quaternions pop up. So Professor Hitzer, Boujard, Debye, Seinwald, and Scheuermann, I should have put dots here as well, many people working on Fourier transforms. And another reason is that the quaternions, they also pop up in the conformal algebra. So conformal geometry, the conformal geometric algebra, is in a sense also related to quaternions. So it's quite recent, these fields. Fueter's original result. dating back to 1935. What he did is what I put in a box here. He defined a map from holomorphic functions to these regular functions. And I should explain what the map does. Well, the input is a holomorphic function in the complex plane, mind you. So it's f of z. So z is a complex number, x plus high y. So it consists of a real part and an imaginary part, f of z. So it's in the kernel of this Cauchy-Riemann operator, a holomorphic function. The output of the map is a Q-regular function. Q-regular, as on the first slide, it means the solution for this particular differential operator. And how does it work? How does the Fueter map work? Well, you get a function in quaternions as follows. You start from the holomorphic map f, small f here. It consists of u and v. You see u and you see v. What you do is to replace x and y by the t and the rho that I wrote down here. So the quaternion can be written as t plus rho omega. You plug in the t instead of x, the rho instead of y, and instead of the complex unit I, vector, the square root of minus 1, you put the vector omega. So it's literally a translation. But then you need to act with this differential operator, the Laplace operator. And just to be sure that we all know what we're talking about, the Laplace operator would be dt squared, dx squared, dy squared, and dz squared. So the Laplace operator, wave operator, I don't know how you call it. So it's a combination of two things, a substitution and an action of the Laplace operator. But this function that you obtain here, as it looks here, sits in the kernel of this operator. So you have a map from holomorphic functions to Q-regular functions. That is basically what Fueter's theorem says. Now the idea is to put this in a higher dimensional setting. And the higher dimensional setting is called Clifford analysis. Now if you have never heard about Clifford analysis, it's easy to explain what it basically amounts to. It is somehow inspired by an equation coming from physics. And the equation is the massless Dirac equation. Mind you, massless, that would be not for electrons. I guess neutrinos have spin 1/2 of this. So, but this is the equation that is usually studied in physics, and it is the physics notation. So Feynman, the d/ notation, gamma mu delta mu. The idea here is that these are matrices. So one of the things that Dirac realized in 1928, 1928, is that in order to take a square root of a Hamiltonian, you use matrices. But these matrices, they generate an algebraic object, which is called the Clifford algebra. And it has indices 1 and 3. 1 and 3 that is related to the underlying orthogonal space. So space-time, Minkowski metric, 1, 3, 1, 3, it's the same. But as you may know, Clifford algebras exist in much greater generality. Instead of 1 and 3, you can choose any two numbers, p and q, well, positive integers. It can be 0, that's okay, but p and q, there exists an algebra for any p and any q Clifford algebra. You can also take a complex version. If you complexify this version, this algebra here, you get a Clifford algebra, which is a complex Clifford algebra. Now from now on, p plus q is always equal to m. That's the dimension of my underlying space, m. Now, this operator here, gamma mu delta mu, it generalizes in any Clifford algebra. Take your favorite RPQ, you can define a differential operator. So this is a first order differential operator. These are partial derivatives, taking the partial derivative with respect to all the coordinates. And these are the generators of this algebra. So this operator here in the box generalizes this operator there, which is Dirac's original operator from 1928. And so what Clifford analysis really wants to do is to study, that's the last bullet here, you want to study functions in the kernel of this Dirac operator. A Clifford algebra, you may know the generating relations. I just quoted them here. So actually it's easier to look at this sentence here. They're all complex or hyperbolic units. So there, for each vector EA, if you square that vector, you get plus or minus 1. If it's complex units, they all square to minus 1. Think of I, j, and k. They all square to minus 1. But it is anti-commutative. So that means if you swap two vectors, you get a minus sign. It's anti-commutative because it's 0 if A is not equal to B. So the anti-commutator is 0, and they're all complex or hyperbolic units. Using these relations, it's actually pretty easy to see that if you square this operator, so that means squaring this operator here, what you will get is the Laplace operator in m dimensions. So here on the blackboard I wrote delta 4, but in m dimensions it becomes delta m. And so Clifford analysis in a nutshell, the Lange, Brax, Sommen, you study functions with values in that Clifford algebra, or a subset thereof, which are in the kernel space for the Dirac operator. That is what we do. A few reasons why we are interested in this function theory. Well, first of all, it generalizes classical complex analysis. Why is that? Well, this is a particular example of a Clifford algebra. So it has one complex unit. So basically, it's the complex numbers. The Dirac operator on R2 factorizes the Laplace operator in 2 dimensions, which means that there is a Cauchy formula that even holds in arbitrary dimensions m. So this is one of the reasons why people study Clifford analysis. It is complex analysis, but in higher dimension. At the same time, it also generalizes quaternionic analysis. I started the lecture with quaternionic analysis. Clifford analysis is even more general. Why is that? Well, an easy way to see it is this particular algebra here, 0, 2, is precisely the algebra of quaternions. And so in the same vein, the Dirac operator in 4 dimensions factorizes this Laplace operator. So Clifford analysis goes further than just complex and quaternion. It has any dimension. Now, here you have holomorphic functions in the classical complex case, holomorphic. Here, quaternion analysis, we have made special solutions. How did we do that? We started from here and we went to quaternion, Fueter's result. So the obvious question is now, if we start here and we can go there, can we go even further in arbitrary dimension? So that means, how can I generalize Fueter's theory? So what I want to do, just like in quaternion analysis, is special solutions, but I want to start from holomorphic functions. Obvious question number 2 is, what can you do with it? And does it have a special meaning? If you have these special solutions, what is the meaning of them? There are already answers out there. The Fueter theorem has been studied before by many people, I would even say. I will here just quote the work of Sommen, my ex-supervisor, Professor Tao and Anakao. I understood that they visited ICU University in February. But I don't know whether Tao was also here.
No, only Anakao, and she didn't have time to give a lecture, but maybe she next time.
So here you can see I wrote down Fueter's theorem essentially in the same box. I've got a map, and it maps solutions for the Cauchy-Riemann operator, holomorphic functions, to solutions for the Dirac operator. It has the very same flavor, kernel to kernel. And essentially, I go to this bullet here, it is the same trick. It's a substitution together with a Laplace operator. Now it was first done in odd dimensions, m, and only later in even dimensions. And it's easy to see why. Here you have a differential operator to a certain power. Now if m is an odd number, then m minus 1 over 2 is an integer, which is perfectly defined. However, if m is an even number, then here you get a fractional power of Laplace. Fractional power of Laplace, you can define it, but then you have to use Fourier multipliers. So it's not a classical differential operator. This is why even dimensions were only considered later. First it was in odd dimension. And then there's a whole bunch of further generalizations, so-called shifted versions. I will not go into detail here. What I want to do here is to describe what this Fueter substitution actually is. So as you can see, the image of the Fueter map is defined in n variables. And it again uses the u and the v. So that is your complex function that you start from, the u and the v. And instead of now doing this way of writing a quaternion, I can do it in the Clifford version now. So we go from a quaternion, this is in H, to something that sits in Rm. So it's a vector x. Did I underline it? I did not. So this would be a full vector. J goes from 1 to m. Now here you have like one coordinate and then all the others. Here I will do the same thing. So I choose one direction separately and then all the rest. So x1, e1, and so forth to xn minus 1, en minus 1. So just one and then all the others. And here I again do a polar decomposition. Polar. So here I again write rho omega. Now omega is of course a unit vector in n minus 2 dimensions. N minus 1 dimensions. So the sphere Sn minus 2. But the idea is the same. You split it. You take one direction and then all the others, and in the other directions you do a polar decomposition. And again, these numbers are substituted instead of the x and the y. So x and y become xm and rho, which is now a radius. And then the unit vector again pops up there where we have to write the complex unit. So it's a similar system. Only this time, the power of Laplace is getting bigger. It makes sense because in the classical quaternionic case, we had a first power. 3 minus 1 is 2 divided by 2 is 1. This time we get this power. So my plan now is to give an alternative proof for this theorem, whereby I use symmetries for a differential operator. And then I will see how far I get depending on the time. So this is an important slide. What are symmetries for a differential operator? So let's say we are looking at a differential operator here, mat call D. It's a differential operator, so it does derivations. And just to be safe, let's say smooth functions from Rm to Rm, and they take values in a certain vector space. Why do I write V here, V arbitrary? Well, they can be numbers, complex numbers, they can be quaternions, they can be Clifford algebra, I don't care. Spinor space, just a vector space. Now, a symmetry, or even more, a generalized symmetry, is a certain endomorphism on the smooth functions. So it maps functions to functions. That's what it does. And it is called generalized symmetry if you can find another mapping from functions to functions, such that this box will hold. So if you first do delta 1, and then you act with the operator, it's the same as first acting with the operator and then delta 2. Now, why is this important? Well, delta 1 preserves solutions for D. It's easy to see. If I start from something which is in the kernel of D and I act with delta 1, and if I want to test whether it's still in the kernel of D, well, if I act with D, D can jump over delta 1. This becomes delta 2, but it's not important because D gives me 0. So this is important. A generalized symmetry, this is the reason why we call it a symmetry, it preserves the solution space. So in physics, this is of course very well known. You want to start from special solutions, and then you use symmetries to generalize all solutions. Note that delta 1 and delta 2 can be equal. It may happen. In that case, it's called a symmetry. If they're not equal, it's called a generalized symmetry. First order symmetries always span a Lie algebra. This is quite classical. Miller wrote a book on it, Symmetries for Differential Operators and Separation of Variables. It was later used in a variety of contexts. So wherever you have special solutions for differential operators, it may be cylindrical or spherical coordinates, it always boils down to using the symmetries of the operator. And what I will do is to look at the symmetries for my Dirac operator. So I am asking the question, which delta 1 and delta 2 can I invent that preserve the kernel of the Dirac operator? First of all, it's very easy to see that the translation symmetry operators are symmetries. So translation, as you know from the Taylor series, is generated by a partial derivative. Now obviously these two things commute. So by definition, a partial derivative maps a solution to a solution. So it's a symmetry. Secondly, they are rotationally invariant. So I wrote this as this relation here. The Dirac operator commutes with these objects here, dLeiy. Now dLeiy acting on a function, here's a tech title, it works like this. It is not too important to remember the precise formula for the action, it's just a detail. It's important to realize that it basically defines a rotation. So Eij in a sense is an anti-symmetric matrix, if you would do it in matrix notation. So basically the relation that I wrote down here says, if you got a solution for the Dirac operator, you can rotate the solution and you still get a solution. How do you do the rotation? Well, like this. It defines an action of the orthogonal Lie algebra. Thirdly, another type of symmetries, Euler symmetries. Now this may need some extra explanation. The Euler operator, which can be defined as RdR, maybe it's easier to look at this definition. So you make a derivation with respect to the coordinates and then you multiply back with the coordinates. So the eigenfunctions for the Euler operator are homogeneous functions. In a sense, it measures the degree of homogeneity. This is a generalized symmetry. So this is delta 1. 2 Euler m minus 1. Here you see 2 Euler m plus 1. It's not a typo. Minus 1 plus 1. It's not a typo. It tells you that you have a generalized symmetry. This would be delta 1. This would be delta 2. But still, solutions go to solutions. So I still have a symmetry. For those of you who are familiar with Lie algebras and representation theory, so far you may recognize rotations, multiples of R, that would be the last one here, and then Rm. Rm, why is that? Because here I have an index, partial derivation with respect to the coordinates, and I have m of them. So this is Rm. So these are the Euclidean motions, rotations and translations. It's a parabolic Lie algebra, if you're familiar with that. That's not too important. The thing is, there's even more symmetries. Now, in order to define these symmetries, I have to say something about the inversion. Maybe the easiest way to introduce the inversion is to mention that the power of, like this one is 0, z is of course a holomorphic function, but the same is true for 1 over z, which is the fundamental solution. So what I did here is an inversion. A similar thing applies here. So I have an inversion. The I refers to inversion. And it maps solutions to solutions, as you can see. And how does it do that? Well, I give you a function. You have to change the arguments. This is precisely like it is in the complex case. And you multiply with this factor here. This is how the inversion acts on a function which is in the kernel of Laplace operator. Now, because you can verify that this particular combination holds, so if I first do the inversion, then Dirac, and then the inversion again, I get Dirac up to this factor here. This allows me to get a new class of symmetries. So the new symmetries are the combination inversion, derivation, inversion. It is indeed a generalized symmetry. As you can see, this is delta 1. This is my operator. This here, this whole expression here, a bit more complicated, is delta 2. But my operator is there. So I again found new generalized symmetries. If I now put them all together, I get the full...
May I ask, this is a transversion already?
That's the transversion.
Okay.
Yeah, okay. If you are familiar with the term transversion, these are transversions. So it is inverse, translate, inverse, transversion. And this here. Well, you have to take the exponential, but that would be the transversions. True. So the full conformal picture, and the word conformal here refers to conformal invariants or conformal Lie algebra. We have found 4 types of symmetries. I started with translations, I added rotations, then I had this Euler symmetry, and I finished with transversions, inversions composed with translations. So that's 4 types of symmetries, and they define a Lie algebra. What does that mean? Well, if you take the commutator, so this bracket here, this is the commutator bracket, just to be sure, commutator bracket of A and B is AB minus BA commutator bracket. If you take the commutator of any 2 symmetries, you get, again, an element sitting somewhere here. For example, I take a translation and I take a transversion. If I calculate their commutator, I get a rotation together with maybe a factor here. I say maybe because it depends on j and k. If j is not equal to k, I get a rotation. If j is equal to k, I get this factor here. But it again belongs to this algebraic object, which has a name. It is this Lie algebra. It's the Lie algebra of conformal symmetries. If you are familiar with Clifford algebras, these are bivectors. Bivectors in the Clifford algebra 1 and plus 1. In abstract form, this is how it looks like. So it's a 1-graded Lie algebra. That's how they call it. I will not use this, but just to be sure. Now, a very small intermezzo, the Lie algebra SL2. You should be familiar with this from linear algebra, but just to make sure, SL2 has a classical matrix definition. So it's 2 by 2 complex matrices, and their trace is equal to 0. So as a vector space, there's a famous basis. So the 1 in the upper diagonal, anti-diagonal here, a 1 down here, and then of course if I want to say something on the diagonal, then I have to put 1 and minus 1, because it has to be traceless. These 3 matrices are classically called X, Y, and H, or sometimes small e, small f, and small h. It depends on the textbook that you use. I stick to capital X, Y, and H. Now, it defines a Lie algebra, and why is that? Because there's a bracket. So again here, the commutator bracket. And if you calculate the commutators of these matrices, you get these classical relations. The commutator of x and y is h and x is 2x, h and y is minus 2y. Basic linear algebra. So that is the simplest, it's also a simple Lie algebra in the mathematical sense, the simplest Lie algebra, which is used in the classification. I will not only use the Lie algebra itself, but also certain representations for it. Now, don't be scared from this slide. What I do is I take a certain vector. I call it VH. Now, VH should be in the kernel of X. So X is an operator in a representation. It should kill my vector. And then I do a repeated action of Y on this vector VH. So as you can see, VH, I repeatedly act with Y. 1 time, 2 times, 3 times, and so forth, infinite times. What I get is a new vector space, provided that this is always different from 0, because otherwise it stops somewhere and then I get a finite dimensional representation. Now, this object that I wrote down here is quite well known in abstract linear algebra, and it's called a Verma module. It can have an arbitrary index lambda. And you may ask yourself, where is the index lambda coming into play? Well, it is because each of these vectors is an eigenvector for h. So if h acts on one of these vectors here that I just made, I get this eigenvalue. So if j is equal to 0, I get the maximal eigenvalue, and then they go down by 2. It's maybe actually easier to draw such a Verma module. So I start from VH. VH is killed by x act trivium. And then I use y to make y VH, and then I make y squared VH, and so on. And I keep doing this until I have an infinite string. So it's like an infinite string. Now, x will always act in this direction, and h gives me eigenvalues. So h acts like this, and here h acts like this, and this gives me the eigenvalue lambda. And that is why I note there's something in a kernel, and then let this factor act on the element in the kernel. That is a Verma module in the literature. So classical Lie algebra matrices, and then the classical abstract Verma modules. Now I apply it. How do I do that? Well, I can make SL2, this matrix algebra, in a completely different way. So it's still x, y, and h, but as you can see here, it's made in a different way. A partial derivative, so the generator of a translation, a generator of a transversion, and then this Euler combination. If you would calculate the commutator of these three operators, you would still get a copy of SL2. So this is another realization for this Lie algebra. And I can make Verma modules. How do I do that? Well, I have to start with an element in the kernel of x. So it's on the blackboard here. VH should be in the kernel of x. Now my VH will be this polynomial. Now as you can see, the polynomial only depends on x1 through xm minus 1. So obviously it's in the kernel of dxm, the last one. Oh, I chose j equal to m. So then it's in the, oh, typo number 2. This should be m here instead of j. Actually, this is a very bad thing. If you're a mathematician, you should think about your indices. There's a j here, a j here, a j here. Very bad. This j here should be an m, not a j. So I take an element in the kernel of partial xm, and then I let I act to make an infinite string. But I is this here. I is the transversion. So my transversions create a Verma module. So it's infinite dimensional, and this is the number lambda. It's the eigenvalue of the element which is killed by this operator here. This here, I come back to that later. Gegenbauer polynomials, don't worry. I will now do the same thing as before. What do I mean by before? I go back a few slides. Inversion. Inversion, kernel to kernel, a function, and then you see here a factor divided by a power of the norm, and then x divided by x squared. This slides, but then more advanced. That is to say, the only difference here, I put it in red, is that I put an extra alpha. Where is the extra alpha? The extra alpha is here. It's the only difference. X over x squared, x over x to the power m, but I put here an extra alpha, complex number. And the typical case of interest is alpha equal to minus 2L, but L a positive number. So it's minus 2 times a positive number. Now previously I told you that the inversion maps solutions for Dirac to solutions for Dirac. It was a symmetry after all, so it has to map solutions to solutions. This particular operator here with this extra alpha has different mapping properties. So the mapping properties differ from the Klein inversion. The Klein inversion, previous case, would have been alpha equal to 0. For a different alpha, that is to say for alpha minus 2L, you can see I still go from a kernel to a kernel. Still works. However, my operator has changed. It's no longer the kernel of Dirac, it's the kernel of a power of Dirac this time. It's easy to see because you introduce an extra power of x in the denominator. So you need an extra factor to be killed. That is why I need the power of the operator here. And this is what I will use. Why is that? I still have a copy of SL2. Similarly as in the previous slides, I can make SL2 with a translation, a kind of transversion, although it's not a transversion in the classical sense anymore now, and then the commutator H. Now this operator here, this difficult combination, the transversion, so to say, has an explicit form which I wrote down here. Maybe this is an excellent point to say that it is first order in x. So this is a derivation, it's minus 1, plus 2, so that's plus 1. This is plus 1, and this is plus 1. So it's an operator which goes up in the degrees of homogeneity. This operator I will use to prove the Fueter theorem. At that point I use symmetries to prove Fueter's theorem. Now Fueter theorem, recall, has two ingredients. I need a substitution map, and I need a Laplace power. So I need to be able to map a complex number to a Clifford number, and then I need a suitable power of a Laplace operator. But it is easy to guess how the substitution map looks like. Earlier results, that means summon, tau, cow, and so on, they all have a substitution which is based on the observation that a complex number u plus iv goes to u plus omega emv. So in a sense, you map a scalar to a scalar plus a bivector times a scalar. That's what you do. Complex number, Clifford number, but it's a special Clifford number. It's a scalar plus a bivector. But if you have studied Clifford algebras, you probably know that a scalar plus a bivector is the result from the multiplication of two vectors. If you multiply a vector and a vector, that is exactly what you get. So this suggests replacing the complex number by the product of two vectors. So what I do is to take my vector x, my Clifford vector, and I multiply it with one special direction. You may ask yourself, how do you choose the direction? Well, I already did. When I wrote down this, I already chose a special direction here. So actually, this vector here is the one that I choose here separately. So I literally already made this choice. And so this is the result. It's a scalar, and this are bivectors. So this is precisely what I want. And now I have a very easy proof. This is Fueter's theorem in one page, actually. These are complex powers, z to the power k, after the substitution. So just to make sure that you understand this, z, the complex power, goes to this combination, x times em with a minus sign, that bar. So basically, this here is z to the power k, after my substitution. It is quite easily proved, I didn't do it here on the slide, but it's quite easy to prove that if this particular operator here acts on the power of z after a substitution, you get the next power. So you go from k to k plus 1. Okay, you get a constant, but you basically go from zk to zk plus 1. But if you look at this particular operator here, as it stands here, it looks like it just drops out of nowhere, like the proverbial rabbit from the hat. However, if you compare it with this expression here, you see minus norm squared partial derivation, xm, and then 2 Euler plus a certain number, and then this wedge here. If you compare that operator with the operator, which I wrote here, it's exactly the same. Minus norm x squared, partial derivative, xm, 2 Euler, a number, and then the wedge. The only thing I did was to choose a good alpha. Like the previous slide had alpha plus m minus 1, something like that. So I have to choose an appropriate alpha. Now the alpha that I have to choose is 3 minus m. So this relation here, this relation says that this particular combination, it's like transversions, to a certain power, give me powers of z. K factorial because of this, but powers of z. But I showed you earlier that this operation here, this special inversion I alpha, preserves solutions for powers of Dirac operators. Now I 3 minus m is equal to I minus 2l. Remember, I was interested in minus 2l. Well, 3 minus m is equal to minus 2l if l is equal to this number. Note, this only works for m odd, which already appeared on the previous slides. That also worked only for m odd. But I know that this operator preserves solutions for this operator here. So 1 plus 2l, if I plug it in, 1 plus 2l is the power, Dirac power n minus 2. So this means that this combination here, inversion and then the partial derivative inversion, preserves solutions of this power here, Dirac to the power n minus 2. So the conclusion is now that this here, these powers of z after the substitution, are in the kernel of this operator. However, I can rewrite it like the power m minus 2. If m is odd, I can write it as a first power, and then should this not be m minus 3? Is there another typo on my slide? No, it should be this power here. So what this says is that this combination here, this combination, is in the kernel of this operator. So this is Fueter's theorem. It tells you if you start from a complex power z, z to the power k, first you do a substitution, and then you have a power of Dirac. And the result is something which is in the kernel of this operator. So I get a monogenic function. But this is true for all k. Actually, I never used the exact value for k. And as it holds for all k, it holds for all holomorphic functions. So what I did here is to show you that if I start from a holomorphic function and I replace z by this particular combination and act with this power of Laplace, I get a monogenic function. Now this is the time where I will ask the chairman what the time is.
Oh yeah, you still have 6 minutes.
And then it's 13:40.
Yes.
Yes. So maybe let me skip the slides and show you that what Fueter's theorem really does, and this is a connection with Gegenbauer polynomials. So this is a particular kind of orthogonal polynomials. You may know them from either a class and representation theory or special functions, Gegenbauer polynomials. In a sense, what Fueter's theorem does, this is a holomorphic function. So it is powers of z, a certain combination, like a Taylor series. It maps it to combinations involving Gegenbauer polynomials. So the special solutions which arise in Clifford analysis because of Fueter's theorem are special solutions which can be expressed in Gegenbauer polynomials. There is a different way to see why Gegenbauer polynomials arise, but in order to do that, I need branching rules, and in order to do that, I need representation theory, and I cannot do that in 5 minutes, so I will not do this. However, I will tell you that the different interpretation for Fueter's theorem leads to a few questions. So I said that Fueter's theorem basically says that complex powers are mapped to special components for the restriction of homogeneous solutions. Well, that would have been the previous slide, I didn't tell you. I have to rephrase it. Complex powers are mapped to special solutions which can be expressed in terms of Gegenbauer polynomials. But this is essentially the slice monogenic function theory developed by the Italian school, Stupak, Colombo, Sabadini. Now, an obvious question is whether I can do better than just a restriction from Rm to Rm minus 1. So the m minus 1, just in case you're wondering, pops up here. So I have a vector in Rm. I take one direction aside, and then I have all the rest. So that's m minus 1 directions. So the question is, if you take